Thanks for the,
I'll put the
So, thanks for the attention. Sorry for the delay. My talk is, I wasn't sure how long this presentation was, and this is meant to be somewhat of an interactive or sort of a brainstorming about optimizations for dynamic languages. One of the areas that I've been working on recently is characterization of dynamic languages and performance of dynamic languages on modern architectures, on current architectures and systems. And so what I wanted to present was some of the differences in the workloads that occur for dynamic languages, such as Python, Ruby, PHP. What we've observed there, and what are the opportunities for better optimizations in GCC, given the types of characteristics of different types of code that exist in these languages compared to, let's say, a spec benchmark or a web server, and maybe get some feedback from the audience about areas that GCC can be improved in ways to tackle the performance challenges that these languages present. So basically, I'm going to give a little bit of an introduction about the languages and then give sort of alternating back and forth between some characteristics and some optimization opportunities, and hopefully get some more discussion about that. So basically, as I said, this is about options for scripting languages, dynamic scripting languages, interpreters, and this is providing more and more workloads moving to these types of languages, and more use away from Java, and just the popularity of these languages is increasing. This is sort of a background slide. This isn't the latest information about the popularity of languages, and C and C++ are alternating first, but in general, one can see these dynamic languages making a large amount of progress and inroads in the usage for applications. And it's used for the flexibility of dynamic typing, high-level data structures. To a large extent, it's actually used because of the very extensive frameworks and libraries. In other words, Ruby is very popular because of Rails, and Python is very popular because of Zope, Django, there's NumPy, there's a sort of slightly wider use there. PHP obviously has a great deal of use within web servers. Python is very popular within Google, available for Google App Engine. A lot of PHP is used inside Facebook, so there's more and more extensive use of these languages and opportunities for optimization and for improving the performance, especially these very large scaled-out systems, whether it be YouTube or Facebook or Twitter, use of Ruby. So what are the characteristics? This is a comparison of spec and on the right, spec in the middle, spec FP in Python, and what you see one of the big differences in these languages, especially CPython and applications running in CPython, that's what Python means there, is the functions are much smaller. You have a larger number of functions compared to the spec, which is where many companies, many compilers have focused in the past. There's a big difference in the size of functions. This isn't Fortran calling these functions, a lot more abstraction, a lot more individual functions being called, doing less work. So the question there is what can be done where there's more overhead in the application, more overhead in the function call overhead for a large number of small functions, and what can be improved. So here's another example in CPython. Is what's the common path? And you can see that there's a Python benchmark that Google developed called Unlabeled Swallow, and that some of the more realistic benchmarks are Django and Ruby. And if one looks at the profile of this application, the largest function, the most important one is PyVal frame, which gets about 25% of the instructions, but then very close after for all of these realistic applications, there's some that are more floating point intensive, numerical intensive, which show different characteristics. But right after that is this function called look-dict string. And look-dict string is actually an optimized version of a general dictionary lookup for strings. And what happens in that function actually is there's a very common case for very unpopulated dictionaries. That it will, assuming that it really was a string, it'll go through, it'll calculate this hash, and then normally find the value it wants if it's there in the first bucket. So the common case is just immediately finding that key and returning it. And then there's a lot of this uncommon case, which is what happens in a lot of these dynamic languages and their implementations for interpreters, which is to focus on, to have specialized cases for fast paths. In other words, in most of these dynamic languages, all of the values, for instance, are boxed. And so it will then have a fast path for doing, let's say, an integer add, and not call it the general dynamic calculation of what's the type of this variable, and in the most general case for performing, let's say, a concatenation with an addition operator instead of an add. So there are a lot of special cases that occur either in the dispatch loop or in the implementation of functions. And the problem here is that there's a lot of overhead in the APIs for Power, for x86, for all of these different processors and targets to handle this uncommon case. There's a lot of additional saved registers, and so it's like you can see this difference here of all of this additional stack that is calculated, created here on the left, and all through for the case where it may call look-dict. So this is a lot of overhead in memory allocation, memory traffic, and all in preparation for the unusual, uncommon case of actually calling into the general look-dict if it didn't happen to be a string, or if it didn't happen to find the object in the first bucket. So this gets to one optimization that we've been starting to implement in GCC of shrink wrapping. And one can see if GCC's implementation isn't powerful enough yet, but if one takes that uncommon case that I showed at the beginning and manually separates that out into another function, all of a sudden that huge amount of stack allocation and traffic for the uncommon case here drops away extensively and all goes into this look-dict string special function. So all of a sudden you get a much improved, much smaller overhead for the stack allocation. So the question is, can we improve, for instance, the implementation of shrink wrapping in GCC to be able to capture these types of cases automatically, which occur in dynamic languages, trying to specialize common cases because of the inherent overhead slow performance of these interpreters. So this is sort of a characteristic of the implementation of interpreters of these languages, and here's one opportunity that provided a substantial performance improvement. And as I showed here, this is the second most important function, 5% of the current cycle time without that optimization, and it drops down to be much more efficient with this type of manual outline, but which is not possible to be done manually for all of these applications, and this is an opportunity for automation and better optimization in the compiler. Another characteristic of these dynamic languages is that they have very different performance behavior in branches. There's many more branches and many more forward branches, and in most processors, the assumption is that a backward branch will be taken and a forward branch won't be taken. So this difference in behavior for dynamic languages is actually fighting against the processor's assumptions and can benefit from additional hints, from additional profiling and feedback through whatever hints the processor or assembly language allows to better characterize the branch behavior, the branch history table, better populate that in the processor. So this is another difference in the behavior of dynamic languages from more traditional high-performance computing or transaction database types of workloads. So as I said, the better branch prediction, branch hints, and options for better utilization of profile-directed feedback to improve the control flow information to better balance or match the processor's behavior. Another work that Jan Vitek and a number of people working in JavaScript characterization, dynamic language characterization, is that even though these are dynamic languages, the actual behavior of the language itself, of the programmer, the call sites really aren't as dynamic. So one can see that the percent of the call sites that are actually polymorphic versus non-polymorphic for a large number of websites. This is JavaScript. So this is switching from Python to JavaScript, but a large number of popular websites, and one can see that in percentages, almost 100% of the call sites are non-polymorphic. So this is, there's a single call versus how many had multiple callings to different functions, different actual instances at the call site. So, I mean, other than Facebook, Google Maps, Gmail, Twitter, it's not very dynamic in the real behavior of the application. So again, is this an opportunity for GCC to do additional devirtualization, additional opportunities to optimize the calls to these functions based again on profiling that the functions really aren't as dynamic as the programmer would. Yes?
So it reflects the real use of polymorphism, or just the code that is written is not polymorphic?
No, this is the dynamic.
Actually, the real use.
The real use. No. The code is written often in the general case, but the real use is that the code, that there is some small tail at the end. That in Jan's paper, there's actually 1 or 2 functions that have 10,000 different functions, different instances called at the call site. But that was just 1 or 2 and very rare versus having tens of thousands, 100,000 calls of at a call site to a single instance of a function. So again, devirtualization, specialization, more opportunities for profile-directed feedback for the behavior, the real behavior of the application, which doesn't have the dynamism that is inherently available or isn't currently, for whatever reason, developers aren't utilizing or writing the code in to leverage the full dynamism of the language. Yes, Stan?
Just to chime in for a moment, I think that in a way is perhaps not surprising because now it's likely to be written with a particular data type in mind.
Yes.
And you're using dynamism as a way of future-proofing, but here and now, you're doing a string algorithm or a numeric algorithm.
Exactly, but the point is exactly that because people are future-proofing, are writing it in this dynamic language, but aren't writing dynamic code, this is now an opportunity, and what can the compiler do based on this knowledge, based on the way that people are actually programming the language as opposed to the most conservative, possible way that the language is utilized. And again, it requires profile-directed feedback or some sort of guards because, this call site could change, it could become more dynamic, but if there are only, a single at best, or just a few, 1, 2, 3 different functions that are actually the instances that are called at this call site, how can the compiler generate more efficient code for this specific, case and knowledge of the use as opposed to for the more general, jumping into anywhere. You can do some sort of a small, decision tree, small direct calls, and again, if you're, I know that Intel has done some work on being able to sort of devirtualize indirect branches, but if one can perform these as the compiler can convert these into direct branches, that improves the branch history and the processor as well. So again, transformations that the compiler can do to actually produce better performance in the real implementation and usage and running of these applications. So, then another question is, okay, well, JITs will just solve everything. I mean, it's all going over the JITs. We'll just, and one of the main projects that I've been working on at IBM is an intro project called Fioronto, where it's very similar to Google's Unladen Swallow project, which was connecting up, in IBM's case, IBM's internal JIT that we use for our Java implementation to the CPython as a virtual machine, converting CPython bytecodes directly into, translating into the JIT and utilizing the JIT to try to improve the performance. The same way that Unladen Swallow connected the LLVM JIT to CPython. And 1.0 here is CPython 2.6 performance. And so this is comparing IBM's JIT, US's Unladen Swallow, PyPy, and Jython is, if you're unaware, a converting Python to Java, running in the Java VM. And this Java VM is also, again, running on IBM's Java VM. And so, Jython, the current version of Jython has actually improved things a little bit. I mean, so it's not as bad as we see here, but you can also see in this that IBM's Fioronto project is basically duplicating the results that Unladen Swallow achieved. It's a little better because Unladen Swallow specifically didn't want to make modifications to CPython. IBM made some additional optimizations in CPython, which allows the performance to be a little bit better. But basically, using a traditional JIT, a JIT that was designed for Java or for a statically typed language, pretty much hits a wall. And doesn't show a lot of benefit. And the hope, the assumption was that if one could translate the Python code or this other dynamic language code into a method JIT, a very powerful, effective method JIT, and then could inline all this with the JIT's own profiling based on the actual behavior of the real application as it's running, perform enough inline and see enough of the code, eventually it could see through all of the various helper functions to improve the behavior and get in substantial speedups. And what people have seen is that PyPy, this is PyPy 1.7 here, has achieved a lot of performance with a custom JIT. It's a tracing JIT, but that the traditional JITs have not been very effective at improving the performance. The issue here is not so much what JITs can and cannot work, but again, the way that PyPy actually functions, and here's another set of benchmarks, Richard, which again shows PyPy showing a lot of performance. Just in back on PyPy achieves about 5.5 times better performance across a wide variety of benchmarks. Unladen Swallow and Fioronto getting maybe like 2 times better, 2 to 3 times better, if not less. So what people are doing because of these limitations of the JIT so far is using various types of conversions. There's Cython, which is a tool mainly for writing CPython extensions. You write it in Python and converts it to C or C++. Facebook developed their something called HipHop, which is a conversion tool for taking PHP code, their PHP code, and converting that into C++. PyPy is actually a translator, and all of these translators are being then compiled by GCC or G++. So this is a lot now of machine-generated code for these languages, which are becoming much more popular. The question is, what can be done for this type of behavior as GCC extends from being not only a direct target for languages C, C++, Go, Fortran, Objective-C, but now is being used as a target for optimizing these conversions. Even PyPy, the way that PyPy works is it is written in Python, actually it goes through a translation process. There's a JIT, but the JIT is created by this big Python source code, multiple files that are all run through Python and converted into C. It's written in a subset of Python. It's not as dynamic. It allows static type analysis of the code, so it can be converted into a statically typed language, and it's converted into a language that is C compiled by GCC. So this is now a very large amount of machine-generated code that all of these dynamic attempts at improving the performance of dynamic languages are generated. So, as I mentioned, they're creating basically large decision trees, deterministic finite automaton. There are large, number of switches, basically traversing the internal states of this virtual machine that they've created. That then will most of the time, the hope is, will spend most of its time in the JIT, and it's itself generating machine code, and as I showed, showing large performance improvement, but when it's falling back because of a guard failure into the interpreter, this is an opportunity for GCC to affect the performance of these systems. There's a large number of also user labels. I mean, I guess Richie's not here. We had this discussion a few months ago where a problem that PyPy had in performance degradation was because GCC specifically wanted to preserve user labels and didn't want to allow certain movement of code across user labels. And we had a discussion about how that restriction could be reduced, because this was technically a user label, but it wasn't a user label that the Python developer cared about. This was a user label that was artificially created by the translation code, but yet was inhibiting an important optimization, of loop optimization, and slowing down some high-performance computation that PyPy was actually able to perform well. So it's that sort of question that we can start raising of, given this different type of code that is going to be presented to GCC from an interpreter, from this type of translation for dynamic languages, what optimizations can GCC develop or focus on that will improve the performance of this code? So I don't know if people have any additional ideas. We can continue to discuss that. Another issue that was raised by the GCC, by the PyPy community, is because they're actually using a fully garbage collected system. They have difficulty accessing, just finding the roots. They basically have, for x86, they're using a special GCC ASM statements and just sort of groveling through the GCC assembly code to figure out what the roots are. For every other architecture, ARM and PowerPC at the moment, they're using something called a shadow stack. They're keeping the roots sort of in parallel. And a fallback is the bone garbage collector. The bone garbage collector is about twice as slow as the shadow stack one. But one request they made is some way in GCC to be able to provide hints or to be able to provide feedback for their JIT and their infrastructure to find the roots, the garbage collection roots of the code that GCC is generating, which are values are actually pointers and which are just other random values. So that's another opportunity for GCC to provide assistance for these languages. And another piece they're actually working on right now, because of the connection between the JIT and the interpreter calling other native functions, the traditional CPython modules, and C-type, I think, is working with FFI. And so the foreign function interface that is available through the GNU project. And so one question there was how to allow perhaps automatic introspection of the objects that are being created in a more efficient interface between the Python code and some native code, instead of using going through the somewhat cumbersome FFI interface, and obtain perhaps being able to directly look at the interface of the function that's being called and having the JIT, let's see, parse debugging information, some symbol table information, knowing what the types are, knowing what exactly the interface is, and then dynamically generating the codes to call into the function as opposed to going through FFI and just packaging up all the arguments and unpackaging all the arguments and the sort of standing on one's head and one does for FFI. So one piece that they've actually been working on is this new CFFI interface, where it's not automatic introspection, but it's an improvement where one can actually embed C code now in the the Python code, either declaring structures, declaring variable types, declaring calling out to various functions, and it can directly load up these dynamic libraries and call into them without going through a sort of improved FFI module. And so that's basically at either the ABI level, as they were saying, or the API level, being able to better interface with the C or native functions. And so that's sort of the list of characteristics of these languages and the challenges that they're faced and that present to both GCC and opportunities for GCC to be able to improve the performance of these languages and have some sort of a market or an opportunity here for better performance with Python, Ruby, allow better interfacing with these languages, and hopefully provide some unique facilities and capabilities that will continue to allow these languages to improve their performance and utilize GCC. So that's basically a summary. Any questions, or if people have any other suggestions or comments about how GCC can be better optimized for this?
It sounds to me like we might benefit from adding benchmarks to the test suite, where the result of the benchmark isn't that it works, but whether the performance is degraded or improved. So we can see what their changes are actually having an effect on these benchmarks. And you could have, for example, some of the large...
You mean contributing to the benchmarks of these communities, or these communities contributing benchmarks to GCC?
My idea was to have benchmarks be part of the GCC test suite. For example, Drive, and then you can see the performance changes, how if GCC is getting better or worse, according to these particular applications. And if that became part of the mainstream, my patch does this, by the way, it improves performance with this benchmark, or oh dear, it makes this pipeline thing run slower, maybe I should be checking the kit.
Yeah, under the left range hand, spec, everybody says voting for perspective.
But
Spec left, or whatever, we need some.
Well, but there are some, Perl bench and spec actually is somewhat representative of this. Mike, certainly there's similar huge functions with huge overhead. Again, I mentioned the problem with string wrapping. This is actually a problem or similar to something that happens in Perl bench. And as far as the machine-generated code, GCC actually, machine descriptions are actually produced this way. Going through that, not only the scheduler, the DFA that's produced for the scheduler, but actually the whole machine-generated code for instruction selection in GCC is not that different than the code that, for instance, Python is generating by its translator. So improvements that we make to the performance of GCC itself will be able to better optimize, for instance, the instruction extract and all these files that the GCC itself creates will also improve the performance of PyPy Cyclone, this other machine generated code. So not only will it help these other, it will improving GCC own performance for these aspects, and GCC already has, because its performance in GCC, we already have spent some time optimizing this type of behavior, but it'll help ourselves. It'll help reduce GCC's performance problems and challenges by trying to address some of these similar code examples and challenges.
Yeah, you were mentioning about Workbench, and thinking about it, I haven't yet come to a jailed conclusion. But I've been thinking that rather than just plain shrink wrapping, where you're assuming that you just test an argument and then do the rest of the expensive function, you want to possibly move down to basic blocks and have basic blocks then do the save registers and restore registers, rather than doing it all in parallel. And that would help a lot of the interpreter-intensive parts of the benchmarks I would imagine.
I was kind of intrigued by that, because essentially it's an argument against inlining if you can identify rare functions. And it makes a lot of sense, but I'm thinking, what do people do for that now?
Well, I mean, it's one of these things, damn if you do, damn if you don't. One of the things we see now is very small functions, where you do some of these stores, you do some more calls and then return. The store queue actually, it'll stall waiting for the store queue because it has to do the stores, and then the loads have to wait for the stores to come back.
But even again, I mean, this is the the Intel code. I mean, this is, I don't know if HJ has any comment if the latest IP bridge processor will just be perfectly fine with this or not. But I'm sure that less memory traffic. I mean, I don't know how much they're doing with the virtualization of the stack in the x86, but all of these unnecessary pushes and pops can't help.
So does that pan out in reality? I think because from the programmer's point of view, what you're saying is that if people take the rare cases and stick them off in separate little functions, their program gets faster without doing anything else.
But
I've never actually heard of that happening.
yeah, but if, Stan, in some of these cases, it's that you have 1,000-line switch state, and you have 500 cases in the switch state, and one case happens to need all 50 registers, and most of the others only.
No, that's what I say. As sort of an abstract thought process, yeah, that makes sense. But I'm wondering if that actually.
No. This actually understanding for this example, it did actually work because for this case, what happened is I did this outline because we had seen in other cases that this register saving and restore was a problem. So I actually outlined it this way, and this isn't actually exactly what I wrote. Because when I wrote it this way, GCC inlined it again.
You have to explicitly say.
I had to annotate the function to explicitly say no inline in this function. These.
So it seems like.
And after I did that, then I did get about 10 to 20% speed up for that one
I say it's
function.
interesting. It's an interesting data point for programmers that may actually be like not getting their advantage here,
Right.
not being very good at it because GC is inlining behind their back, because supposedly inlining is always good.
It seems like what offers me the panacea for this is the profile directed feedback and the feedback directed optimization where you, and I don't know if this is difficult or it's done, but for Mike's example of the switch also having feedback that is
Right.
common switch, and so take out the
Exactly.
switch.
Well, I mean, not just that, but as you're saying, it's, this is another place where one needs to essentially reach across GCC's intermediate representation boundary. Because part of this is understanding from the target description what is actually going to be the cost of this call or this inline, because some of this requires large number of registers, and without getting some feedback out of the register pressure, the number of registers you're going to have, if you're doing this inline just at GCC's gimbal stage. You know, it all looks good, and we're just, you know, and it's, you know, we need to be more careful about the, you know, the register pressure, the register lifetime, and are we creating a, you know, an unnecessary, you know, register lifetime over a common function that doesn't actually need this or
I
common.
mean, I don't know, so I'm
Yeah.
not actually
Well,
so, but I mean, it seems like the obvious answer there is for, profile directed optimization, you know,
Right.
not just do, you know, block ordering and, you know, the sort of range mission kind of stuff, but also the large scale inline decisions and those kinds of things. All your examples would be
Right.
like that.
But it really, I mean, you don't really know with profiling whether, say, inlining this function would end up optimizing to nothing, right? This is a possibility, so it's really hard to decide whether, you really have to try both cases and see what's better than just collecting profiles.
And of course, it may be different on different machines too. But, you know, it occurs to me that we may want to start reaching out to people writing machine generated things, Python and so forth. You know, they may be using a distro that's 3 or 4 GCC generations old and don't know about our new nifty attributes or something like that.
So basically, the summary is I'm just trying to point out that in the way that people write interpreters, I mean, I didn't go back and look at, you know, the original, you know, in the, you know, Bash or you know, Perl or some of these old, and see if they have these exact same characteristics, but at least with newer versions, newer dynamic languages, these special cases that are being written for, you know, the common cases specifically are trying to utilize less overhead. I mean, they're expecting the common case, expect they don't necessarily need to look for every single error case, and the GCC, if this is all packed into a function, either because of the user writing a single large function, or because GCC is inlining a lot of smaller pieces, smaller helper handlers into this main function, it may end up creating a lot of additional prolog and epilogue action, you know, stores of loads that are unnecessary for the common case through the function. What we in IBM call this in some ways is sort of de facto leaf function. You have a function that really is a leaf function in the common case, the way it's actually being is it's either a de facto leaf function or it's a de facto tail call, in which case it doesn't need to perform all of this overhead. But because of the ABIs that require where there's a single prolog and epilogue prior to our work on shrink wrapping, one is performing all this additional overhead for the uncommon case of either an error handler or some more complicated fallback routine. If, for instance, in this case, you know, the hash, you know, you need to follow through the hash and do a more complicated comparison to actually find it out. So the question is, can you know, ways for GCC to better optimize for this type of code, which people are writing in interpreters because of either what they're observing or what they're expecting to be optimization. And clearly, if they write these special cases, it improves things somewhat. In other words, if you don't need to go through the full, you know, complicated handler of you know, unboxing a value, reboxing, doing some operation, that's going to provide some speed up, but the full speed up is being inhibited because of these penalties that the ABI compiler are introducing. And so how can we help these developers avoid that? Yes.
What about built-in expect? And I would expect this to help shoot patterns.
Yes.
Did you measure some of it? Did you try, for example, on this example, it looks to me like it is already known if the special case is a rare error handling path, which should not happen usually, or if it's a fast path, it's going to be executed most of the times. So it would be easy to add built-in expect.
Yes.
And so,
I've been trying on this, and I'm not sure if how built-in expect interacts with the shrink wrapping.
I would expect that if you have built-in expect there, and it should help the shrink wrapping. If it doesn't, it sounds like, no.
Sounds like a fix.
Well, actually, the built-in expects interacts with the function splitting, and if you put the expect there, then the function will be split, and then we will inline it again. So if you prevent the inlining, then it will just work. So, how hard would be to put together some kind of benchmark suite for these type of things? Because the way I'm tuning the inliner is basically looking on the benchmarks which we have, which are kind of biased. We have specs, we have the C++ benchmarks, which are basically trying to show up that we are not inlining enough. They are always pushing the limits up, and we don't have this type of stuff in our radar. So, I was recently analyzing a similar problem on the Povray, which is also technically interpreter inside, and yeah, that's precisely the same situation there. So it would be nice to have some simple benchmarks added.
Yeah, we could definitely work on that. I mean, as you said, to try to get some artificial ones, maybe not having to build all of Python out of Python takes that long. But
Well, we can't build Python, if we have some interesting benchmark. I think it would be a good addition to the benchmark which we have.
yes.
So in Go we have the bytecode interpreter, and this is really where we like just see who's granting. And so this interpreter is like a build function, the jump table, and the tuples. And in some cases you would notice that you see, for instance, the jump table will be stored on the stack instead of the register, which is not efficient. So we have manually instructed to actually store it in a register. And this is the kind of thing where probably GC would help by, I don't know, if we could provide more hints about what we expect or something like that.
Steph?
So, one of the things that is sort of interesting about the scripting languages and the overall picture in the web context is that I think the general assumption is that the overall time between the squids and the database queries and so forth, the actual execution time of the script is going to be relatively small. But I don't know if you or anybody else has heard of any numbers, is it 1% of the total?
Well, it depends on the language. PHP is actually often that way. PHP has other overhead problems in the way that most people use it. It's spending, I agree, it's spending most of his time in the database. It's actually reparsing stuff, and I'm blanking on the name. There's some PHP accelerators which basically sort of save the parsed version of the file. Python and others can save the compiled bytecode, so that it is not as much of a problem. But for Python now, one can actually now have web servers written in Python, and pipelines are actually using that. So they actually are spending more time. Django and Rails are actually spending more time in the dynamic language itself now. It's not just only spending time on the interpreter. Quora, is a website that is written all in Python. They switched over to PyPy, and I think maybe a good speed up from that. Facebook is completely written in it's very common. In PHP, they wouldn't have converted over to using hip hop, and they're still actively now looking at HHVM. They now are trying to do there's multiple reasons for